Welcome everyone. In this video, I will be covering section 11.7, strategy for testing series. Section 1 was about sequence, section 2 to section 6 were all about series, and we saw several tests so far to test the convergence of the series. Some of them were test for divergence and comparison test, limit comparison test, and how geometric series and P series could be applied in comparison test, because we know the convergence when the geometric series converges, when P series converges, and so on. We also saw integral test. We also saw some series such as alternating series, where the terms are change sign alternatively, positive and negative, or negative and positive. Then we apply how we applied alternating series test. And then we also saw something about conditional convergence, when a series is said to be conditionally convergent, and all that were covered in the earlier sections. Now, this section is about strategy, which means that looking at a function, looking at a series, how we decide what test to apply and to decide whether the series is convergent or divergent. So, if the series is of the form sigma 1 over n to the p, which is a p series, we know it converges when p is more than 1 and diverges when p is less than or equal to 1. If it is geometric, then it converges when common ratio absolute value is less than 1 and diverges when the common ratio is more than or equal to 1. Absolute value of the common ratio is more than or equal to 1. Then if the series is of the form similar to the P series or geometric series, then the comparison test should be considered. If an is a rational function, so if it is a polynomial over a polynomial type, then the series should be compared with the P series. In order to compare to the P series, we take the series to be compared to by creating a series by looking at the given series and taking the highest power of n in the numerator and the denominator. Then it will turn out to be a P series where the P will be either greater than 1 or less than 1. Then if sigma an has some negative terms as well, then we can apply the comparison test to sigma absolute an and test for absolute convergence. If right away limit as n approaching infinity an is not equal to 0, then the test for divergence should be used. If the series has alternatively positive and negative terms, there's negative 1 to the power n minus 1 involved, then alternating series test is an obvious option. If the series sometimes involve factorials, in which case you will apply the ratio test. If an is of the form something to the power n, then automatically root test may be useful. If an is f of n, where f of x is the relating function, then integral, and if integral 1 through infinity, if this improper integral is easily evaluated, then integral test is an effective method. For all of this, for some of the tests, there are some conditions required to be proved. And so if it is integral test, for example, we have to show that it's positive continuous and it is decreasing on the interval 1 through infinity. So there are some requirements for certain tests like alternating series as well. So if there are some requirements, you have to prove those requirements and then apply the test. So we will see some examples. Example 1, it's only asking that simply indicate which test should be used, but we will try to prove as much as we can these problems. The sigma n minus 1 over 2n plus 1, if you look at this, it's kind of a rational expression in n. So the easiest test that we can always try is the test for divergence. So without the sigma, This is usually the nth term. So consider a limit as n approaching infinity of an, which is limit as n approaching infinity, n minus 1 over 2n plus 1. Now we divide the numerator and the denominator by n. So if you right away apply infinity, then it will become infinity over infinity type. So we have to divide by n. So it becomes limit as n approaching infinity. So the numerator would be n over n, which is 1, minus 1 over n, divided by 2n over n, which is 2, plus 1 over n. 1 over n will approach 0 because it's 1 over a large number. Same 1 over n here approaches 0. So it is equal to 1/2, which is clearly not equal to 0. Therefore, by test for divergence, the series diverges. Always make sure what test you apply and what your conclusion is. If the test requires something needs to be proved in the test or something, some conditions need to be established, then you have to establish those. Now, next example, sigma n varying from 1 through infinity, square root of n cube plus 1 divided by 3n cube plus 4n square plus 2. So you notice here the expression is again rational. The test for divergence may not work here, so we will apply limit comparison test or comparison test. Limit comparison test may be a better option here. So we have to choose first to, if you are able to recognize what is to apply, mention that apply a limit comparison test, LCT. So we have to choose the Bn to compare to sigma Bn. We have to choose sigma Bn. So sigma, the highest term on the numerator divided by highest term in the denominator. We can choose like this. And by choosing this, we are going to bring this to the P-series form. So it is sigma n to the power 3 halves divided by 3n cube. So it is sigma. 1/3 is after all a constant, which can be taken out. So it is 1 over n to the power 3 minus 3 halves, which is 3 halves. So which is a P-series with P equal to 3 halves, which is more than 1. So which means that it is a convergent P-series. So now we have chosen a series by choosing the highest power of the numerator over highest power of the denominator. Then we are going to apply now the ratio, the limit comparison test, so which is an over bn, and then taking the limit. An over bn, an is square root of n cube plus 1 divided by 3n cube plus 4n square plus 2. I'm dividing by bn, and then bn is this expression here. After you reduce it gets to this one, but keeping it square root of n cube over 3n cube is easier. As we are dividing, so you're going to flip and multiply. So it is 3n cube divided by square root of n cube. So we get an over bn equal to square root of n cube plus 1 over this n cube, everything within the radical. Then the numerator is 3n cube, then we will take the denominator for that one as 3n cube plus 4n square plus 2. As we are going to take limit as n approaching infinity in the next step, we will reduce this. It's n cube over n cube, so which is 1, then 1 over n cube. Then for this part, we will divide the numerator and the denominator by either n cube or 3n cube. So we get this multiplied by a 3n cube over n cube, that gives a 3. Then 3n cube over n cube, that gives a 3 as well. And 4n square over n cube, that gives 4 over n plus 2 over n cube. So when you apply limit as n approaching infinity, an over bn, and it becomes limit as n approaching infinity, 1 plus 1 over n cube within the radical times 3 over 3 plus 4 over n plus 2 over n cube. So here, 4 over n approaches 0, 1 over n cube approaches 0, 1 over n cube approaches 0. So the whole thing reduces to, the first part within the radical is 1. Then we have 3 over 3. So the whole thing becomes 1. So this is equal to C. C is finite and positive. Therefore, by limit comparison test, the series sigma an or the given series converges. In case you have forgotten what limit comparison test is, it applies to series of positive terms. So if sigma an is the given series, and if sigma bn is the chosen one, chosen series for which you know the convergence or divergence of, and if limit n approaching infinity of an over bn equal to c, where c is finite and positive, then sigma an and sigma bn behave alike. Then sigma an and sigma bn converge or diverge together. By that what we mean is if sigma bn converges, sigma an would converge as well. Or if sigma bn diverges, sigma an would diverge as well.